Our last topic in this lecture series is isomers. You have actually already been taught about 2 different isomers. I just need to show you one more and summarize what we know. Isomers are different molecules with the same molecular formula. You've already been introduced to constitutional isomers. These have different connectivities. Then there are stereoisomers. These have the same connectivities, but a different spatial arrangement. There are many stereoisomers, but we're going to introduce in this class geometric isomers, which are cis and trans, and enantiomers, which are non-superimposable mirror images. Constitutional isomers have already been introduced. If you were asked to draw C4H10, you might draw the linear butane compound, and this has a connectivity where we have CH3s on each end and 2 CH2 groups in the middle. Compare this to 2-methylpropane. This has 3 CH3 groups. Their condensed formulas are different. They have different connectivities. Therefore, these are constitutional isomers. Geometric isomers can be reintroduced by thinking about 2-butene. The condensed structure shows CH3s at each end and a double bond in the middle. However, we can draw this structure like this, where the methyl groups are opposite one another, or like this, where the methyl groups are on the same side of the double bond. So their condensed formulas are the same, meaning they have the same type of connections and bonds, but spatially they're different. The isomer on the left is known as trans. So if you draw a line between carbons 2 and 3, and then draw the hydrogen groups, you can see that they are on the opposite side of the double bond. The isomer on the right is known as cis. If we draw that line between carbons 2 and 3, you can see that the hydrogens are on the same side of the double bond. Sometimes students ask me, well, how did you know where to draw the hydrogens? Well, we know that the 2 middle carbons have 3 bonds, so we need to draw 1 hydrogen. 3 bonds means 3 electron regions, which means our bond angle is 120 degrees. So it wouldn't make sense when we draw in that hydrogen to draw it here. Clearly, this bond is close to 120 degrees. So if I'm going to draw in the hydrogen, I need to try and put that spaced so that the rest of my bonds are 120 degrees. That is why this Z configuration is our trans isomer. And the same argument applies for cis. So back to naming. You were introduced to these 2 alkenes in a previous lecture, but we weren't quite finished with the name. The top one is trans 8-methyl-4-propyl-2-decene. That's because when we draw in the hydrogens, they are on the opposite side of the double bond. The bottom one is actually cis 8-methyl-4-propyl-2-decene. That's because if we draw in the hydrogens, you notice that they are on the same side of the double bond. So cis and trans come at the front of the name. So let's try a little bit more naming. We'll start with the one on the left. I'm going to number the carbons closest to the end with the double bond. And it doesn't matter if I put the 6th carbon as the one down or the one to the side. I still get 6 carbons. So this leaves me with hex. It's got a double bond, so the ending is an -ene. The double bond starts on the 2nd carbon. On the 5th carbon, we have a group of 1 carbon, so that's a methyl group, giving us 5-methyl. And finally, you notice the Z configuration here, which means if we add the hydrogens, they will be on opposite sides of the double bond. So this is trans 5-methyl-2-hexene. Notice that the dashes go between the letters and the numbers. Now let's try the one on the right. I see 7 carbons, so that is hept. It's got an -ene ending because it's got a double bond, and that double bond starts on the 3rd carbon. On the 5th carbon, we have a 1-carbon group, so that gives us 5-methyl. And finally, if we draw in the hydrogens, they are on the same side of the double bond, giving us cis-5-methyl-3-heptene. So back to this compound which you started to name in the previous lecture. We weren't quite finished. You need to add a cis or a trans to this. Now let's look at the next type of stereoisomer. This is the new one to introduce to you. And you notice I have a picture of a hand on the slide. And if you look at a mirror image of your hand, you notice that the pinkies match up and the thumbs match up. But what if you rotate your right hand 180 degrees? Is it superimposable on your left hand? So you can try this while you're watching, and I hope you realize that, well, no. I've got the thumb of my left hand matched up with the pinky of my right hand, and the pinky of my left hand matched up with the thumb of my right hand. And of course you know this. If you try to put your left glove on your right hand, you notice that it doesn't fit properly. So these are what's called non-superimposable mirror images. Molecules that are like this are termed chiral. Chiral comes from the Greek word chier, as your hand is also a non-superimposable mirror image. So how do you find enantiomeric stereoisomers, which are chiral? One way is to have 4 different groups on carbon. Now, first off, carbon's in the middle, and we have 4 different groups around it: a hydrogen, fluorine, chlorine, and bromine. This would be a very difficult molecule to synthesize, but it's a simple place to start. So here we have the mirror image of this molecule. And the question is, if you rotate it 180 degrees, is it superimposable? Meaning, do all the atoms match up in the same place? And I hope your answer is no. The hydrogens are in the same place to the left. The fluorines are in the same place at the top, but this molecule has bromine coming out of the screen, and this version has chlorine coming out of the screen. And chlorine's going back on this molecule, and bromine is going back on this molecule. So if I rotate it 180 degrees, it is non-superimposable. But maybe you're wondering if there's other ways I can rotate this to get all 4 atoms in the same location. Let me show you. I have here 2 enantiomers with 4 different groups on carbon. I trust that you can see that these are mirror images of one another. The yellows match up, the reds on top match up, white is to the bottom, and the atom represented by blue is to the top. So these are looking at one another across a mirror. Here is my proof that you can't turn one enantiomer into another just by twisting. I can try that, but you notice that the blue and the white don't match up, even though the red and the yellow do. Let me try another combination. How about if I get blue and white to match up? Well, I've got those matched, but now red and yellow have problems. Okay, why don't I just try blue and red? Well, now you can see that I have blue and red matched up, but I have a problem with yellow and white. Okay, let me just twist that to fix yellow and white. Well, I fixed yellow and white, but now blue and red have a problem. So that's all 4 combinations. I trust you see that no matter how I twist this, I cannot make all 4 atoms occupy the same place. So this is what's known as a chiral molecule. And these 2 molecules are enantiomers. So they fall under the category of stereoisomers, where they have the same constitution, the same connections, but a different spatial arrangement. Now, what if you have, instead of 4 different groups around the carbon, only 3 different types of groups? So you have a hydrogen, a fluorine, and 2 bromines. Here is our mirror image. And when we rotate at 180 degrees, can we superimpose these? And I hope you answer yes. I have the hydrogens on the left, the fluorines above, and the bromines coming out of the screen and going back in the screen. Now we have exchanged one bromine for the other, but since they're both bromine, we don't know the difference. Let me show you with an actual model. What if, instead of 4 different groups around the carbon, I only have 3 different groups around the carbon? So I have 2 atoms that are represented by white around each carbon, a red atom, and a yellow atom. Can I twist those and make the atoms match up? Yes. I now have yellow in the same spot, red in the same spot, and my white atoms in the same spot. And as you can see, these are superimposable mirror images. So we don't call them chiral, they're identical molecules. So we would call this an achiral molecule. So if you have 4 different groups attached to carbon, you have a chiral compound. If you have 2 of those groups identical, so only 3 different kinds of groups around the carbon, this would be an achiral molecule. Now let's move to a larger molecule and think about chirality. Certainly it can't be any of the carbons from 5 to 10 because these only have 3 electron regions. And it can't be 11 because it has ethyl groups which are identical coming off it. And certainly not 14 because that has a CH2 group, and not 15 because that has a CH3 group. It's carbon number 3 here. It has 3 bonds to it, so we need 1 hydrogen, and now we have 4 different groups. We have this substituted benzene, this ethyl group, and what's known as a methyl group, and of course a hydrogen. So 4 different groups around carbon. Here's another chiral compound. It actually has 2 carbons in it that have enantiomers. There's one here where I've shown the star. It's got 4 different groups around this carbon, and 4 different groups around this carbon. And this is actually the molecule called aspartame, which is in NutraSweet, which is artificial sweetener. It's composed of some amino acids. Funny how that can fool the tongue to make you think that it's sweet instead of a protein. But not everybody thinks that aspartame is sweet, because when manufacturing this, sometimes the mirror image is made, and the mirror image tastes bitter. When I do this for in-person classes, I always ask, how many of you think that diet soda, which has NutraSweet in it, tastes bitter? And usually a few students raise their hands. And my husband would raise his hand as well if he were in the class, because some people actually have more discerning tongues. So, if this whole chemistry thing isn't working out for you, if you think that diet soda tastes bitter, you have a very sensitive palate, and maybe you should go into wine tasting. An interesting thing about chiral compounds is if you have all of one enantiomer isolated, it will actually rotate light. So if you have light that's going through a slit such that it's only at points 0 and 180 degrees, if you pass that polarized light through a sample, you will actually get the light to turn. And this angle in which it rotates at is a measure of the purity. So you should be aware of that, especially if you're eventually going to work in fiber optics or something like that. I want to show you a video a moment which actually shows this using different solutions of Chiral syrup. Would you imagine that sugar could actually be a chiral compound? So the setup for this video is that they have the sugar solutions on a laptop screen, which is typically polarized at, I believe, 45 degrees, and a pair of sunglasses in front of the camera. And they're going to rotate the solutions. So let's go take a look at chiral solutions of sugar.
Here's our homemade polarimeter. It's a computer screen with solutions of water, and then 1, 2, and 3 are increasing amounts of glucose. It's a Chiral syrup. Putting the sunglasses over it. Kathy, can you spin that for me just real slowly? The background is just a yellow from PowerPoint with an arrow looking at the angle here. I think with the idea is maybe later on you could print these out as pictures and then look at the angle and compare that to the amount of light coming through. See, number 3, which has the most glucose in it, is now dark. Again, the W is for water. 2 is now getting dark, and 3 is lightening up, and there's 1 now is going dark. Now the screen itself is going black. The screen is polarized at a 45-degree angle. Now we've gone halfway around. Kathy's doing a real nice job spinning over there. 3 is darkening up again.
It's for you, or someone else going to go watch this?
Well, this is going to go on YouTube, honey. And 3 is dark again.
Number of hits, 2 from David White. Cynthia White.
Okay, now go back a little bit. Yeah, go back a little bit more. A little bit more. Okay, keep on going then. Now the screen itself is dark there. And then we're right back where we started. Very good. So now you can analyze the angular polarization based on the darkening and lightening there of the different concentrations, different amounts of syrup there.
So you can see that something as simple as Chiral syrup has some chiral character to it. So here is your mission for your last few lecture questions. Looking at the picture above, are they constitutional isomers, stereoisomers, or the same molecule? As a reminder, constitutional isomers have a different connection of atoms, whereas stereoisomers that you've been introduced to are cis-trans or enantiomers. For this one, notice how the oxygen is in the middle for one compound and on the end for a different compound. All right, how about this example? These 2 molecules in the box, are they constitutional isomers, stereoisomers, or the exact same molecule? Question 5. I hope you notice that you can rotate these to look the same. Question 6. How many different groups do we have attached to the carbon? Are there 4 different groups or less? And how about this one? Notice we have 2 different hydrogens off the double bond for the right one and 1 hydrogen off the double bond for the left one. And finally this one. How many different groups are attached to the carbon in the middle? So congratulations, you've now made it through all the content I'd intend to present for Chem 101. There's one more lecture. It's a review lecture to help you study for your final exam.